and I want to know the same question, 6 meters long, 100 watts, and if a person is sitting 3 meters away from the center, what is the sound intensity that they hear? So we're going to set up the integral similarly. Go to integral dp over 4 pi r squared, and then you're going to have dp is equal to lambda dx over 4 pi r squared, and then the r represents the distance from a piece here all the way to that point here. So the next question to ask is, does the r change as this piece goes from here all the way to here, right? Is the distance r changing at all? Well, it does look like this is closer to here than this is, right? And then if a piece is here, then that's farther away, and if a piece is in the center, that's the farthest away, right? So it does seem like it is changing. So if it is changing, the only thing we can pull out of this is the 4 pi, right? But the r squared has to stay in the integral. So you're going to have integral lambda dx over r squared. So then it will matter if the sound intensity here is uniform or not. That will make a difference. So because we have to find the function for r and then relate it to the x, and then therefore it will matter if the lambda is uniform or not. So in the case of the uniform, we could pull it out of the integral, and then we'll just have lambda over 4 pi integral dx over r squared. Then we have to come up with a description for r. So we can see here, make a triangle like this. This is the radius of the circle, and then here you have r, and then this is 3, right? And then this angle here will define, this species is r, and this angle here will define as theta. So I've done a similar problem for electric fields and for electric potential in chapter 23 and 25. So this will resemble that same problem. Okay, so then we're going to use the law of cosines, and we're going to say this is 180 minus theta. So I'm defining this angle as theta, and then this, by virtue of that, would be 180 minus theta. So then you're going to have the law of cosines applied to this. R squared is equal to r squared plus 3 squared minus 2 times r times 3 times cosine of 180 minus theta. Alright, so then you're going to have r squared is equal to r squared plus 9 minus, and then this is going to be 6r, and then cosine of 180 minus theta is going to be negative cosine theta. So then this becomes negative cosine theta, and then changes this to positive cosine of theta. Okay, so then we can put down what the big R was. Remember what the big R was? The length of the semicircle was pi r, which was 6, and then r was equal to 6 over pi. So we can say r squared is equal to 6 over pi squared plus 9 plus 6 times 6 over pi cosine theta. So there it's going to be 36 over pi squared plus 9 plus 36 over pi. And then you're going to have here cosine of theta. Okay, so then we can put that down here. We have I is equal, right? However, this is still not in an integrable form, right? Because this angle theta and the x, we have to find a relationship between the two, because we can't integrate two different variables in an integral, right? So the next thing we say is that the distance from the center of the rod, right, to any portion here is x. Remember when we were doing the straight rod, we put the xy axis at the center, and then we took a piece, and then we defined the distance from the center to any piece as x, right? That distance. So since the rod is curved now, like this, so then the distance from the center to that piece becomes x. Then we can use some geometry. We can say this arc length here, and then this looks like this. This is x here. This distance from here to here is x. This is r, and then this is theta, is the subtended angle. So then we can say x is equal to r theta. Then we can substitute that there, right? So we're going to have x is equal to r times theta. And then dx is equal to r times d theta. So what does dx represent? It represents this little thickness, right? Like this. Little piece here. This is dx. Then you have a little piece like this, and then this is d theta. So what you're saying is that if you take a little sliver of an arc length, and then it subtends an angle d theta, the relationship between the arc length here, dx, along the edge, dx is equal to the radius of that sliver, r, times the subtended angle of that little small piece, d theta. So then you're going to have dx is equal to r d theta. And then we can factor that out, right? So then, now this is in an integrable form. So what are the limits of my integral? Well, we can integrate from 0 to pi over 2, right? From here to here, and then we can double it because it's symmetrically distanced away from here. So we can go 0 to pi over 2, and then we can double it. This portion here, I can simplify a little bit more. I can say, let's see here, since we're doubling it, the 2 cancels the 4, we get a 2. And then we have here power over 2 pi. The L is L. And then the radius, remember, it was equal to, L was equal to pi r, which when the radius substitute L over pi. And length will cancel this length. And then that means we don't even need to put the length out here. We don't even need to put the radius. They cancel. So we just end up getting p over 2 pi squared. And then we're going to have to integrate that. Okay, so let's integrate that. That's 2. Right? Then we're going to multiply that by the p over the 2 pi squared. Okay, so I is equal to p over 2 pi squared times that number, 8.164 times 10 to the minus 2. And then the power was, remember, 100 watts. So right? So it is definitely, the intensity is much less than the intensity was at the center, because we went 3 meters away. That's quite a bit distance away. Actually, visually, since the radius was 6 over pi, the radius was roughly around what? 6 over 3, that's about 2 meters, right? The radius was 2 meters. So 3 meters away visually is even farther. So it should be something like this. Right? So we went quite a distance away, so the intensity drops quite a lot. So if we change that to decibels now, it was 123 decibels at the center, so it went all the way down to 116 decibels. So that really makes sense, right? So now we'll do the case where it was non-uniform. It will make a difference, right? So the 2 ends are the more louder ones. They're closer to the person, and then at the center is very silent and it's very far away from the person. So it should end up becoming greater than 116.2 decibels, right? Greater than 116, because you are closer to the louder music which is taking place at the 2 ends, right? So in the next example, that's the one that we'll do, okay? Thank you very much.